Okay, we can go ahead with problem 3.6 now from Wald's General Relativity. He says the metric of Euclidean R3 in spherical coordinates is this expression given here, and we're supposed to calculate the Christoffel symbol components in this coordinate system. So I've already written down the metric in like matrix form here, just because this is kind of easier for me to look at personally. So you'll see, the dr squared component is there alone, so we can just put a 1 here in the RR part of this metric or matrix, and then the d theta squared one is r squared, which is here, and the d phi squared is r squared sine squared theta, which we've got here, and then the inverse metric is similarly diagonal. There's nothing with the cross terms or cross differentials. But I just didn't write the zeros to keep things simple, and so I just have this here for when we actually calculate the Christoffel symbols. It's easier for me to think about things this way as opposed to looking at the line element every time. What you guys do is up to you, obviously. I've also copy pasted the equation that we're going to use straight out of Wald here. So 3.1.30 is our kind of important equation, and to save time, so there are a lot of Christoffel symbols that can be calculated. I'm not going to calculate the ones that end up being equal to 0. So if I don't, calculate a component, you can assume that it is 0. So we're going to calculate r theta theta. We're going to calculate r phi phi. We're going to calculate theta r theta. We're going to calculate theta phi phi, gamma phi theta phi, phi r phi, phi r, theta r. Okay, so let's just get started on the first one. So we have something like this: gamma r theta theta equals 1/2. Now we're going to have to copy kind of what's going on here. So rho and sigma. Rho is r for us, and then sigma is going to be arbitrary, so we can write this as r sigma. D, G, now it's nu sigma, so nu for us is going to be theta, and sigma stays arbitrary, by del x mu, so mu for us is going to be theta, plus del G, now I'm just going to start doing it, theta sigma, by del x theta minus del G theta theta by del x sigma. So okay, we know that the inverse metric is strictly diagonal, so the only time this term that multiplies everything is going to be non-zero is when theta is r. So we can go ahead and fill that in and make all the thetas r's. Or not theta, sorry, the sigma's r's. So it's going to be theta r here by del x theta plus theta r by del x theta minus g theta theta by del xr. Now again, not only is the inverse metric diagonal, but the metric itself is diagonal. So this g theta r is just a 0, and the derivative of 0 is 0, so that goes away. Same deal here. And so the only term we're going to have left is the r derivative of the theta theta component, the negative of that. So this is going to be 1/2. So let's take GRR inverse, and that's just going to be 1. So whatever, we can write it. 1 times negative the r derivative of the theta theta component. So that's going to be the r derivative of r squared. We get 2r. The 2's cancel, and this component is equal to negative r. Now we can look at gamma r phi phi. So again, we just write down our what do you call it? We write down our formula, and in this case, so we get rho sigma. It's going to be r sigma for us, so we know this is just going to be r, and our sigmas are going to be r right away. So let's go ahead and do that. And then we get, through here we get del g phi r by del x phi plus del g phi r again by del x phi minus del g phi phi by del x r. So again, because the diagonal, or because the metric is diagonal, these are going to go away, and we're left with something quite similar to before. So we can have equals 1/2 times, remember this GRR is just 1, and then we have minus the r derivative of the phi phi component. So it's going to be 2r sine squared theta. Once again, the 2's cancel, and we get that this Christoffel component is equal to minus r sine squared theta. Okay, next we can calculate this one. Let's say gamma theta theta r, and because of the symmetry of the gammas, this is going to be equal to theta r theta. So we'll just calculate this once. So again, we get a theta up here, and then we know that the only way this isn't going to be 0 is if we make sigma theta then, so we do that again. We get del g r theta by del x theta plus del g theta theta by del xr minus del g theta r by del x theta. So these off diagonal ones go away. So now we get 1/2, we get the theta theta component of the inverse metric, which is going to be 1/r squared. And then we get the r derivative of the theta theta component of the non-inverse metric, so 2r. So the 2's cancel, 1r cancels with the square, and we get 1/r for both of these Christoffel components. Okay, next we can try gamma theta phi phi. So again, because the theta is going to be up here, it's going to have to be theta theta. That's what's going to take over the sigma. And we get del g phi theta by del x phi plus del g phi theta del x phi again minus del g phi phi by del x theta. So very similar to before, these are going to go away. We get 1/2. This is going to be 1/r squared again. And then we get minus the theta derivative of the phi phi component of the metric. So that's going to be r squared times the theta derivative of sine squared theta. So we get r squared 2 sine theta times the derivative of sine theta, which is cos theta. And now we're able to just simplify this down. So the r squareds cancel, the 2's cancel, and we get minus sine theta cos theta. Okay, so we've got a couple more to do, and these calculations are pretty mechanical, as you can see, nothing too challenging here. So gamma phi theta phi is going to be 1/2. We're going to get phi upstairs here, and then we get del g phi by del x theta plus del g theta phi by del x phi minus del g theta phi by del x phi. So let's kill our non-diagonals here, and we get so phi upstairs is going to be 1 over r squared sine squared theta, and then we're going to get the theta derivative of the phi component, which we already know is going to be 2 times r squared sine theta cos theta, same as last time. 2's cancel, r squareds cancel, one of the signs in the bottom cancels with this one, and we get cos theta over sine theta, but of course this is nothing other than cot theta. Okay, and then we have the last little pair here. We're going to do gamma phi r phi is equal to gamma phi r by symmetry. This is just 1/2 g phi del g phi by del xr plus del g r phi by del x phi minus del g r phi by del x phi. So same routine, we kill these off because they are off the diagonal. We get 1 over r squared sine squared theta here for this term. And then the r derivative of the phi component of the metric, again, is 2r, this is the r derivative this time, so it's 2r sine squared theta. So let's see, the 2's cancel, one of the r's in the bottom cancels with this r, sine squareds cancel, and we get 1 over r at the end of the day. Okay, so we can start part B now. I just realized I forgot one thing though. For gamma phi theta phi, it's important to remember that this one also has a symmetric component. Phi theta. So we're going to add that to the list up at the top too. Okay. So with that, now we can do part B, which is to write down the components of the geodesic equation in this coordinate system and verify that the solutions correspond to straight lines in Cartesian coordinates. So with that, we're going to use the geodesic equation straight from Wald here. And as you can see, this equation has components in that all that the other, like sigma and nu, are summed over. So the only component that isn't summed over is mu, and that's how we're going to get our components out of this. So the first one is going to be when mu is our r component. And what we get is, so this first term is going to be the second derivative of r with respect to t, so we can write that as r dot dot. And then we get terms for all the Christoffel symbols with r upstairs. So let's have a look. There's going to be 2 in this case, so we get the r theta theta symbol, and then since theta theta is on the bottom, we get just theta dot times theta dot, or theta dot squared. And then we also get r phi phi on this. For similar reasons, we get phi dot squared. And then remember, in part A, we actually calculated these components already, so we can write this more explicitly this way. So gamma r theta theta, if I flip back to that sheet, is negative r. This is times theta dot squared. And then gamma r phi phi, if I look back at my sheet, is minus r sine squared theta. Times phi dot squared equals 0. So we can just simplify this, and then we have our expression. So let's say r dot dot plus, minus r theta dot squared minus r sine squared theta phi dot squared equals 0. And you could factor that r out if you like. I'm not going to bother. The second case then is when mu is our theta coordinate, or theta component. So in that case, we obviously get a theta dot dot as the first term, and then we get terms for every gamma with a theta upstairs. So looking at our list from before, there are 3 such gammas, but 2 of them share a symmetry, so we're just going to exploit that and not write them twice. So for gamma r theta and gamma theta r, those are symmetric, so we're going to put a 2 out front, and then we just get an r dot theta dot. And then we also have gamma, let's see, theta phi phi. So we get a phi dot squared because of the 2 phi's in the bottom there. And this is equal to 0. So rewriting this, we get theta dot dot plus 2. So this gamma theta r theta is, looking back at my page, 1 over r. R dot theta dot. And then this one, gamma theta phi phi, looking back, is minus sine theta cos theta. So again, we can just simplify this. Theta dot dot plus 2 over r dot theta dot minus sine theta cos theta phi dot squared equals 0. I'm just going to check that against my paper. Yes, that looks correct. And then finally, we can consider the last component when mu is our phi. So in this case, obviously, again, we get the phi dot dot as the first one. And then we need to think about terms for all the gammas with phi's upstairs. So there's going to be 4 of them, but it's 2 groups of 2 which share symmetries, basically. So let's say phi theta phi. This is going to have a 2 in front of it because it has symmetry. Do a theta dot phi dot, and then we also are going to get plus 2 gamma phi r phi r dot phi dot equals 0. So again, we could have written this as a term with gamma phi theta phi, and then another term with gamma phi phi theta. But yeah, because of the symmetry, they're just going to end up together. So that's why I have these 2's here. And now let's substitute in our Christoffel components from part A. So gamma phi theta phi is the cotangent of theta. It's theta dot phi dot here. We're going to get plus 2, and then this gamma phi r phi is just simply 1 over r. r dot phi dot equals 0. So again, a little simplification here. And let me just check that 2 code phi dot plus 2 over r dot theta dot. Yeah, so those are the three equations now. And then the last part that remains is to show that in Cartesian coordinates, these equations describe a straight line, if I'm not mistaken. Yeah, that they correspond, the solutions to these equations correspond to straight lines in Cartesian coordinates. So we can do that. I personally didn't do this by hand. I used Mathematica to help me, so we're going to flip over to a Mathematica notebook right now. So now in Mathematica, I can just show how I was able to confirm that the equations that we derived are satisfied by the equations for a straight line in Cartesian coordinates. So the first thing I did was just set up this list of substitutions, basically, where r goes to the sum of the squares of x, y, and z, where I keep x, y, and z parametric in terms of t. Theta is similarly just z over the sum of the squares of those three. And phi goes to this function here, the arc cos of some stuff. So we can build that. And then in this next spot, I just made a list of the three equations that we derived in part B verbatim. I just typed them in exactly how we had them. And build this. And then essentially all I'm doing here is taking that list of equations, making the substitution that we defined at the top, so to get it from spherical to Cartesian coordinates. And then once we've done that, we're making three more substitutions, basically letting x be this function a times t, y be the function b times t, and z be the function c times t, where that will describe a straight line in general. Now I think that you can also do this where x is x naught plus a times t, y is y naught plus b times t, z is z naught plus z is z naught plus c times t. But that was causing Mathematica to choke for me, so I got rid of the starting values and just started from 0. But yeah, besides that, when you build it, it evaluates to 0 equals 0, and we see that all three of the equations are indeed satisfied as it spits out true for all of them.